All right, good morning. Just kind of picking up once again with functions, and I had mentioned last time that we will be looking into sort of a formalized version of what we refer to as the slope formula, and this would be along the lines of what we have with average rate of change of a function, and just sort of referencing a graph from page 163. And there were a couple of graphs, okay, one being a curve and the other one being a straight line. And just kind of taking what we have here, and we have for the curve, okay, we have 1, 6 as a point and also 5, 2. Again, I'm not drawing this perfectly to scale by any stretch of the means, but through the points, let's say 1, 6, and 5, 2, okay, we can say that we have 1, 6, okay, we have the first set of x and y values, and 5, 2 will be the second set. And you have going through these 2 points, okay, will be what is referred to as a secant line. And it's going through these 2 particular points of interest, okay, and now for the secant line, okay, it is going to have its slope, and I'm going to get to this particular graph. And now just for the average rate of change of a function, okay, and we have the function, let's say, be in the form of f of x. Okay, so you have y is equal to f of x. Okay, and we have going from one point to the next. So we have going from x1, y1. Okay, now in functional terms, okay, we have we'll say that the x coordinate we have x01, and if the function, if we have f of x in place of y, okay, now that which is going to replace y01, we have f of x of 1. And we'll say we have for the second order pair, okay, we have x of 2, y of 2, or in functional terms we have x of 2 and f of x of 2. And for the average rate of change of a function, okay, say between 2 specified points. Now, we have, okay, starting out with the slope m, okay, but also in average rate of change terms, we can subscript SCC, okay, alongside the m, and that's going to be what's referred to as the slope of the secant line. And in other words, and what we originally referred to as change in y with respect to change in x, we have in functional terms, okay, we're going to have f of x of 2 minus f of x of 1 all over x of 2 minus x of 1. And again, for the slope to be defined, okay, we cannot have a zero denominator, so we have the condition that the x values cannot be equal to each other. And so just taking what we have for the average rate of change between 1/6 and 5/2, okay, again, we can just sort of formalize, okay, so 1/6, you have x01, y01, and that could also be expressed as x01 and f of x of 1. Likewise with 5/2, okay, we'll have x of 2 and f of x of 2. Okay, and in the case of the secant line, now you're not looking at the slope of the entire graph we have in blue, but we are looking at the average rate of change of the graph in blue as we go from the points 1/6 to 5/2. And so we have for the secant line, okay, we have for the average rate of change, okay, so we have upon first glance, okay, so average rate of change, okay, you have equal to the slope of the secant line okay, so you have f of x of 2 minus f of x of 1 all over x of 2 minus x of 1. Okay. So again, your f of x of 2, your y of 2, that is going to be at 2. And you have minus f of x of 1, which is going to be at 6. And for x of 2 minus x of 1, that's going to be 5 minus 1. Okay, so the vertical change we have at -4. Horizontal change, you have a +4. And for the average rate of change, okay, so we come out to -1. Okay, and again, the average rate of change for that function, again, we have between the points 1/6 and 5/2. Okay, this will come out to -1. And now, again, this is just a formal notation for what we have in addressing slope. Especially whenever you have the graph to be a non-linear entity. And now, in terms of where the average rate of change of a function can come in, and I can provide also a bit of an added visual. And let's say that if you're given, and this sort of ties in what we have with functional values and expressions, and let's say that if you have so you have given a function, okay, so you have f of x is equal to x squared plus 2x and say if we were to determine the average rate of change, and I will say going from, first of all, okay, we say you have going from x equals 1 to x equals 5. Also, second part here, okay, so we have going from x equals 1 to x is equal to 9. Okay, so, and we can tackle both of these parts almost simultaneously. Okay, so we have, just to start out, Okay, so we have f of x is equal to x squared plus 2x. Okay. And again, f of x is a functional notation for what we otherwise say is going to be y. And, okay, now, at x is equal to 1, the corresponding y value, okay, we would have at y is equal to f of 1. Okay, so we're looking at 1 squared and we have plus, that should be 2x. Okay, so we have plus 2 times 1. Okay, so 1 squared is 1. 2 times 1 is 2. And 1 plus 2 is 3. So the point that we have here, when x is 1, your y value is going to be at 3. Now, if we go from x equals 1 to x equals 5, and here for the corresponding y value, okay, so you have f of 5, so that's going to be 5 squared plus 2 times 5. 5 squared is 25. 2 times 5 is 10. 25 plus 10 is going to be at 35. So we have, for that corresponding point, okay, we have 5, 35. And we'll go ahead and tackle our third point involved, okay, which would be whenever x is equal to 9. And for the corresponding y value, okay, so we have f of 9. So you have 9 squared plus 2 times 9. Okay, so 9 squared is 81. And 2 times 9 is 18. Okay, so for this ordered pair, okay, we have 9, 99. All right, and so just looking at what we have for the average rate of change. Okay, so from x equals 1 to x equals 5, okay, so conceptually, okay, you're going from the point 1, 3 to 535. And for the average rate of change, okay, that's going to be the slope of the secant line. Okay. Again, you have your functional notation for y2 minus y1 all over x2 minus x01 for the change in y. Okay, so going from 3 to 35. So we have 35 minus 3 all over x2 minus x01. So this will be 5 minus 1. And so for the average rate of change, we're looking at 32/4. And so the average rate of change between x equals 1 and x equals 5, okay, is going to be at 8. And looking at what we have between x equals 1 and x equals 9, so we still have the same starting point at 1, 3. And we're going from 1, 3 to 9, 99. And for the slope of that secant line. Okay, so you still have same formula, but a different second set of x and y terms. But again, we still had the same first set of x and y values since we're starting from 1, 3 once again. Okay, so for the change in y, so we have 99 minus 3. And we have change in x, have 9 minus 1. Okay, so you have vertical shift upward of 96 units relative to a horizontal shift of 8 units to the right. And we have 96 over 8. And notice we have a higher average rate of change as we go out further in x. Okay, so you have that particular slope, okay, is going to end up at 12. And just to give you a visual and hoping that this graph will show up as, let's see, insert. Yes. Okay. So for what we have in the view, okay, so again we had started out with 1, 3, and again we had our second set of x and y values, okay, respectively at 5 and 35, and then the third set we have at 9, 99. And in terms of average rate of change now for this particular curve, again we have y is equal to f of x is equal to x squared plus 2x Let's see if I can move this. Okay, and in the case of the secant lines, okay, so we're going from, again, from 1, 3 to 5, 35. Okay, so for this line, the average rate of change between x equals 1 and x equals 5. Okay, you have this particular secant line, and once again we'll have for the slope of the secant, the average rate of change, that is equal to 8. And again, we had a different secant slope value going from x equals 1 to x equals 9, where we had it 12. And just as a visual, so you had the entire graph of y is equal to x squared plus 2x, and between x equals 1 and x equals 5, just using this straight line to compute, say like using law of averages, you have the average rate of change to be at 8, at least between x equals 1 and x equals 5. And again, as we venture out further, again, going from x equals 1 to x is equal to 9. Okay, so notice you have a steeper slope, and for the average rate of change in this case, all right, we have going up substantially, okay, from an average rate of 8 to an average rate of 12. And had I ventured out further, let's say to like x is equal to 20, the slope would be even higher. And if I had essentially y to keep on increasing, you could say that the average rate of change would be slowly approaching infinity. But again, as x expands on out to the right, you're going to have the slope to fall into a pattern where it's just going to be continuously increasing. All right. So this is what they refer to by average rate of change, okay, and it applies to graphs regardless of whether they are linear or also nonlinear, as was the case with y is equal to x squared plus 2x. All right, now looking at functions, and right now we've looked at functions on an individual basis. And again, now let's say that if we have operations occurring between functions, okay, so you have a couple of functions. Okay, so you have for functions f of x and g of x. Okay, now we're going to have, just starting out with our operations, adding, subtracting, multiplying, as well as dividing. And we have, first of all, just some of the notations here. Okay, so you have f plus g of x. You have what's referred to as the sum function. And this will translate out to f of x plus g of x. And for what we have in the case of the difference function, for f minus g of x, okay, so you have f of x minus g of x. And in the case of what we have with the product function, okay, so this will translate out to the product of the first and the second functions. In this notation, f of x times g of x. And for what we have in the case of the quotient function, if we have the quotient function in the notation f over g of x, okay, this will translate on out to f of x over g of x. Okay, and now some things we have, just like when we looked at domain for individual functions, we're also going to be looking into domain of operations between functions. And just to kind of cluster together. Okay, now for the sum, difference, and product functions. Okay, now these operations are going to have the exact same domain. Okay, and this domain is going to be formed okay, so you're going to have the domain which will be formed by combining the restrictions. Again, combine the restrictions, if any, of f of x and g of x. Okay, so the sum, difference, and product functions, all these will have the exact same domain. Okay, but now in the case of the quotient function, now the quotient function might have the same domain as the prior three operations, but this one can still have potentially a different domain. And that's because that whatever we have for g of x, the first three operations do not have that restriction that g of x cannot be 0, whereas in the case of f of x over g of x, okay, we have just, looking at it face value, this is not allowed to be 0. So it's on the basis of this, okay, that f over g of x can possibly have a different domain. And just some cases here. Let's say that if we have if we're looking at determining the four operations and their domain. So you're looking at determining those and their domain. And we'll say that we have given, we'll just start out with a couple of linear functions. So you have f of x is equal to 3x plus 7. Then we have g of x is equal to 4x minus 8. Okay, now we'll just look at the operations first, and then we will get to the domain. Okay, so what I'm going to do here, let's copy this portion. Okay, so we have specified. Okay, so we have f of x at 3x plus 7, and we have g of x at 4x minus 8. Okay, so we have for f of x plus g of x. Okay, so we have f of x, again we have 3x plus 7. And we have g of x, in case we have 4x minus 8. All right, so if I add these functions together, okay, and it sort of has a feel of like the factoring by grouping exercises. Okay, so you got parentheses, separating, and you have like an operation of addition in the middle. And but instead of drawing out any common factors, we're just going to add the terms right away. So we have, so you got 3x plus 7 plus 4x minus 8. So removal of the parentheses does not change the signs of any of the terms. Okay, so combining, we have 3x plus 4x. So this will be 7x. And we have 7 minus 8. So this is going to be a negative 1. So the result here we have is 7x minus 1. Now for the difference between the same functions, so you have, again, for f of x, we have the quantity of 3x plus 7. Then you have minus g of x. Again, the reason I'm using parentheses at this stage, okay, is just to kind of show you that we have f of x apart from g of x. Now here we have the operation of subtraction that appears in between. So once I remove parentheses, now we still have 3x plus 7, but taking out the parentheses surrounding g of x, okay, both 4x and negative 8 will be affected by the subtraction in front. So we're going to have 4x becomes negative, and the subtraction of 8 changes over to addition. So in this case, we have 3x minus 4x, so this will be a negative x. And we have 7 plus 8, which is going to come out to 15. Okay, so for the difference of functions, okay, that is going to come out to negative x plus 15. Okay, so just given the nature of the functions, okay, now it is possible for the sum of functions to come out to a different statement, and where the difference of functions can somehow turn out to be, at least the way this layout is expressed, it could turn out to be like where you have the operation of addition between the terms. And again, it's contingent upon the terms that exist, okay, for each of the functions. And for f times g of x, so if I'm looking at multiplying 3x plus 7 and 4x minus 8, okay, so we have upon multiplying, okay, so if I FOIL out, okay, so you have 3x times 4x, so this would be 12x squared. And we have outside product, we have negative 24x. And we have plus 28x. Last product, we have negative 56. And I'll just move down here. So if I combine like terms in the middle, so I'm going to have 12x squared, and I have what's going to be plus 4x minus 56. And in the case of what we have with the quotient function, so you have f of x, okay, which we have right away to be 3x plus 7, and g of x, okay, we have 4x minus 8. And guess what? This ratio is already in simplest form. Okay, and so those would be the resulting operations. Now, for the domain, okay, let me mention, okay, so for the sum, difference, and product functions, okay, their domains, okay, will be formed by combining the restrictions, if any, from the individual functions involved. Okay, so we have with f of x, okay, we have 3x plus 7. Okay, this one we don't have a fraction or an even root radical. And guess what? Since there's no restriction on f of x, now just for f of x individually, the domain is going to be the set of all real numbers. And there's, okay, and we have along with what we have for g of x. Okay, so g of x we have at 4x minus 8. Okay. And this also has no restriction. And the domain is also going to be the set of all real numbers. And guess what? Neither f of x nor g of x will have any restrictions. So that means for what we have in the big picture, okay, is that for the sum function, again, there's no restriction. For the difference function, we have the same thing. And for the product function, again, no restriction, and the domain is still going to be the set of all real numbers. Okay, so the sum, difference, and product functions will all have the same domain. And again, no restrictions are applied. However, in the case of the quotient function, okay, there is going to be a restriction. Okay, so we have for 3x plus 7 over 4x minus 8, okay, we cannot have a zero-valued denominator. So 4x minus 8 cannot be 0. And isolating the x term, we had that 4x cannot be equal to 8. And with division by 4, okay, we had that x cannot be equal to 2. Okay, and so again, you have 2 is going to be excluded, and it will follow that for the domain of the quotient, again, just symbolizing, okay, the exclusion of 2. Think of it kind of like an open circle on 2, ray going to the left and also ray going to the right, and that hole is still locked in at 2, and just translating that in terms of interval notation. So you have parentheses around negative infinity and 2, and that's for those values less than 2, and then we have bypassing 2. You have for the rest of the domain of the quotient function will be the set of values x greater than 2, and this time we have parentheses around 2 and positive infinity. All right, and I'll tell you what, just in the case of just kind of taking what we have for the determination of functions and their domains. And we'll say that we have f of x is equal to, let's say, we have x squared plus 3. And g of x, we'll say, is equal to x squared minus 4. Okay, just looking into the operations here. Okay, so you have given f of x is equal to x squared plus 3, and g of x is equal to x squared minus 4. And if we have, okay, for the sum function, okay, so again, you have f of x plus g of x. So here we have x squared plus 3. From f of x and from g of x again, we have x squared minus 4. And if I were to add together, okay, so there'll be no sign changes upon removing the parentheses. So for f plus g of x, okay, this will translate out to 2x squared minus 1. Now for f minus g of x, okay, now we're looking at the difference between x squared plus 3 and x squared minus 4, and removing the parentheses. Okay, so I have x squared plus 3 minus x squared plus 4. Okay, sign change thanks to the subtraction in front of the g of x. So you have negative x squared and plus 4. Notice we're going to have x squared terms are going to go out. So left standing is going to be a constant, which is going to be at 7. For the product function, f of x times g of x, so I have the quantity, okay, of x squared plus 3 and x squared minus 4. And here we have x squared times x squared, so this will be x to the 4th. Outside and inside products, we have negative 4x squared plus 3x squared. Last product we have at negative 12. Then we have for the output, final output, we have x to the 4th, and then we have minus x squared minus 12. Okay, so this is what we have so far. Okay, so you have the sum of functions. You have with the difference binomial 2x squared minus 1. Difference of functions, we have just a number to result, and that is with the constant 7. And for the product of f of x and g of x, okay, we have a 4th order trinomial. And as for what we have in the case of the quotient function, okay, we have f of x over g of x. And this will just translate out to x squared plus 3 all over x squared minus 4. And factoring the denominator is optional. For what you have already, just substituting. You already had the simplest form since there's no factor other than 1 common to the numerator and denominator. Okay, now for what we have in the case of the domains, okay, so again, the sum, difference, and product functions will have the exact same domain, and this will come from combining the restrictions, if any, of f of x and g of x. Okay, so f of x, you have x squared plus 3. G of x, you have x squared minus 4. And we don't have an even root radical, and we don't have a fraction. So at least for f of x, okay, we have no restriction. And for the domain, okay, so we have the set of all real numbers. This is for f of x, and also for the case that we have for g of x. Had the same kind of scenario. Okay, you have direct expression, okay, for g of x, which we have as a quadratic, also no restriction, so we had the same domain. And since neither f nor g of x will have restrictions. We won't have restrictions for the sum, difference, or product functions either. So we have that bit of history to repeat 3 more times. Whereas in the case of the quotient function, again, g of x cannot be 0. So you have x squared minus 4 cannot be 0. And you can either apply the square root property of equality, or you can just go ahead and factor. So we have x plus 2 and x minus 2 cannot be 0. And from this set of restrictions, okay, we have x cannot be negative 2, nor can x be equal to 2. And I'll just put this forth, okay, just to kind of provide the visual once more. So you have negative 2 and 2 are going to be left out. And so it's going to follow for the domain of the quotient function. If I express in interval notation, so we're going to have 3 subinterval sections, okay, and going from left to right, so you have this, the least of these, you have those values, okay, of x that will be less than negative 2. You have tied in with those values of x between but not including negative 2 and 2. And also we'll have those remaining values of x which will be greater than 2. Okay, so again, the sum, difference, and product functions did not have any restrictions on the basis that neither f of x nor g of x had any restrictions. And in the case of the quotient function, again, we cannot allow a 0 denominator, so we had 2 restricted values whereupon negative and positive 2 were left out. Okay, and let me kind of mention, we'll get a little further into domain in just a moment, but looking at I'll call this part determining I'll call this operational functions and specified values. Now say, in this case, right, say we have given so you have given f of x is equal to x plus 5, And we'll say we have g of x is equal to x minus 2. And we'll say that we have h of x is equal to let's say x plus 10. And say if you were to determine, okay, we'll say that we have f plus g of 5. And we'll say that we have f minus h of 3. And we'll say we have g times h of negative 2. Okay. All right. So again, you have f of x equal to x plus 5, g of x equal to x minus 2, and h of x equal to x plus 10. Okay, I'm going to show you some avenues here. Okay, so first of all, okay, for what we have in the case of f plus g of 5, okay, what I can do here is that for f plus g of 5, okay, this would translate out to, okay, what we have for f plus g of 5, okay, just to kind of set things up. So you can say we have conceptually, okay, that we have f of 5 plus g of 5. So you have f of 5, okay, so this would be 5 plus 5, which would be equal to 10. And for g of 5, okay, now your g of x, you have x minus 2, so g of 5, okay, that's going to be 5 minus 2, which will come out to 3. Okay, and having identified both f of 5 and g of 5, okay, so f of 5 we have at 10. We have g of 5, okay, which we have at 3. And for this outcome, okay, this is going to be 13. So f plus g of 5, okay, this will come out to 13. All right, now for f minus h of 3, okay, so you're looking at f of 3 minus h of 3. So this time we need f of 3 as well as h of 3. Okay, so we have for f of 3, okay, so again you have f of x equal to x plus 5. So we have for f of 3, okay, so this will come out to 3 plus 5, okay, which should be at 8. And for h of 3, now you got h of x equal to x plus 10. And for h of 3, we have 3 plus 10, which would be at 13. And so just fill again for f of 3 and h of 3. So you're going to be looking at the difference between 8 and 13. And here we have 8 minus 13, which will come out to negative 5. So f minus h of 3 comes out again to f of 3 at 8 minus h of 3, which we have the subtraction of 13. And so the overall result, okay, we have at negative 5. Now, for what we have in the case of g times h of negative 2, so again, this is going to be g of negative 2 times h of negative 2 okay, so we have a g of negative 2. So again, your g function, okay, we have x minus 2. So g of negative 2, we have negative 2 minus 2. Negative 2 minus 2 becomes negative 4. And in the case of h of negative 2, again, so referencing h of x, so h of negative 2, okay, this is going to be negative 2 plus 10. And that's going to be a positive 8, okay, and just relaying over to what we have in the setup. Okay, so we're now looking at the product of negative 4 and positive 8. And negative 4 times 8 comes out to negative 32. Okay, so we have in sum, okay, so for specified values, okay, for f plus g of 5, we have f of 5 plus g of 5, and using f of x and g of x to get to f and g of 5, we have those values combined, we have 13. For f minus h of 3, again, I'm using both f of x and h of x, okay, to get to f and h of 3, and taking the difference, we have translating to the difference between 8 and 13, where we have the result at negative 5. And for g times h of negative 2, again, we needed g of negative 2 times h of negative 2 with this approach, and utilizing, again, g of x and h of x, we have those respective values for g of negative 2 and h of negative 2 to be negative 4 and 8, and we have, again, the product to result as negative 32. All right, and just some things to mention about the domain among operations between functions. And let's say that, you know, so far when we looked at domain, okay, with the sum, difference, and product functions, we had unanimously the set of all real numbers, okay, but that would not necessarily always be the case. And I'll just point out an exception. And we'll say that we have so if we're looking at the domain of functions, okay, and we'll just kind of use sort of as building blocks. Okay, say if I have not the operations between functions, just the domain. Okay, say if I have f of x equal to 3 all over x plus 4, and say if I have a function g of x I have x minus 4 all over x plus 1. Okay, and I'm looking for the domain, okay, for the sum difference products and quotient functions. Okay, so I'm just looking for the domain. Okay, so in terms of the sum, difference, product, and quotient functions, especially for the sum, difference, and product, don't worry about adding, subtracting, or multiplying these rational expressions together. Now, if you notice for f of x, okay, we do have a restriction. Okay, since f of x is a fraction and we want to avoid having a zero denominator. And for x plus 4 cannot be 0. And so we have, with this restriction, we have that x cannot be negative 4. For what we have in the case of g of x, now we have x minus 4 all over x plus 1. Again, the burden that is placed upon g of x is that the denominator, just like f of x, cannot be 0. So x plus 1 cannot be 0. So we have that x cannot be negative 1. And if I carry over, let's say the restrictions, okay, now the sum, difference, and product functions will have the same domain. And we're going to have restricted everything that's combined from f of x and g of x. Okay, now for the sum, difference, and product functions, in order to be able to work with f of x, x cannot be negative 4. Now let's do a little bit of color coding here. Okay, and also you have restricted that x cannot be equal to negative 1. Again, so that you can still operate with g of x. Okay, so again, the sum, difference, and product functions are going to have the same domain, and they'll be formed by combining the restrictions applied to the immediate functions involved. Okay, so to be able to work with f of x throughout, x cannot be negative 4. And to also be able to work with g of x, x cannot be negative 1 either. And guess what? For the quotient function, we still had to be able to work with f of x. So again, we have that x cannot be negative 4. And we still had to be able to work with g of x. So we still have that x cannot be negative 1. And again, because we have a quotient function, we still might have a different domain, even though we still had to be able to work with f of x and g of x. And just to see if we do have a different domain, so you have with f over g of x. Okay, so I'm having to get the resulting quotient function on this one. Okay, so I have f of x over g of x. And again, f of x, okay, that was 3 over x plus 4. And for g of x, okay, we had, again, that was x minus 4. All over x plus 1. Okay, now I have a ratio between fractions. And to get out of the fraction over a fraction mode, okay, what I can do here, I can rewrite the division in terms of multiplying. And in doing so if I divide 3x plus 4 by x minus 4 over x plus 1. Again, if you divide by a fraction, it'll be the same as multiplying the bottom fraction in the form of its taking the, let me put it this way, dividing by the bottom fraction will be the same as multiplying by the bottom fraction's reciprocal. So I'm going to flip this bottom ratio. Again, take the reciprocal, and we have just for the result here, so we have 3 times x plus 1, and we have x plus 4 times the quantity of x minus 4. Okay, so again, we have with the original restrictions, now again we have f of x, you have 3 over x plus 4. Again, x could not be negative 4. For g of x, I had x minus 4 over x plus 1, and again, the denominator of that fraction could not be 0, so x could not be negative 1. So x plus 4 can't be 0, x plus 1 can't be 0. And then once we multiply out, notice, okay, x minus 4 was in numerator position, but now upon multiplying by the reciprocal, x minus 4 is now in denominator position. So we have yet another restriction, and that is that x minus 4 cannot be 0. So we have that x cannot be equal to 4. So that means that for f over g of x, we have this added restriction, and that comes from, again, taking the reciprocal of the bottom fraction. So we have the x cannot be equal to 4. And so for the domains, for the domain of f of x, you have only negative 4 is excluded. And for what we have for g of x, okay, you have only negative 1 is excluded. So you have parentheses throughout. Okay. Now, with the sum difference in product functions, okay, we now have both negative 4 and negative 1 excluded. Okay, so just kind of sequencing. So we're looking at those values of x. Less than negative 4, bypassing negative 4, approaching but not including negative 1. So again, we have parentheses. And then for the rest of the set, okay, we have those values of x that will be greater than negative 1. And that will be the same domain for also the difference and the product functions. So, and we have just with the quotient function case, again, the sum difference in product functions will have the exact same domain, and their domain will be on the basis of combining the restrictions of the individual functions, okay, leaving out both negative 4 in reference to f of x and also negative 1 referring to g of x. And then for the quotient function, okay, so I have for that domain, okay, so we're leaving out negative 4 and negative 1. So we have that bit of history to repeat. And now we're also excluding 4. Okay, so we have values less than negative 4, those values between but not including negative 4 and negative 1. Then we have those values between but not including negative 1 and 4. And then rounding out the rest. Okay, we had those values of x which will be greater than 4. And again, for the number of specified exclusions, again, one exclusion, you have 2 subintervals. 2 exclusions, you have 3 subintervals. And then now with the quotient function, we have 3 exclusions, from which we have 4 exclusions. All right, so it's kind of a long interval statement. And now just some items to mention. And there was kind of a typo, and I had for some reason, I don't know why I skipped the 1.4 part, but anyway, I made a little adjustment. Okay, I have sections 1.4 and 1.5 from Alex due Wednesday, February the 17th. I do have video simulations available. And again, on page 225, you can go ahead and look at, once again, 10 through 26 even. I had mentioned that the other day. And also, just a little bit ahead, numbers 47 through 50, 52, 53, 65 through 68, as well as numbers 70 and 76.